I the job part is the bottleneck for me. Actually,
Uh,
my background, I'm in merchant navy, and I have been doing this course uh, when I'm sailing, when I'm home. So uh, as a part time, but that's why I'm looking for that remote job that like somehow I can manage and work my way
yeah,
up to that project. So
yeah, and
that's why I just wanted to ask.
yeah,
Anyway,
I completely understand, but I will share another thing. There's a lot of scope of AI in every field. Even in your
yes, yes.
merchant navy, it has got a lot of scope, whether it is in maintenance or it is for navigation. Okay, it is
Yeah, yeah.
whether basically, so it has got a lot of scope, and you can easily get a senior guy, whether it is your senior XO or senior NAVO or your senior NGO. So they can become easily your guides if you try to find a way.
Yeah.
Okay, okay. Hi, good evening, everyone, and thanks for joining on this revision session for algorithm for data science quiz 2 course. And thanks a lot for joining in. And I would make certain rules very clear in the beginning itself. So it will be basically a discussion. It is not a monologue from my side. It will be a discussion. We will discuss the concepts, and we will mutually we will clarify those concepts. So with that background, I will start, and I will just cover the main important parts which have been covered by the professor during the live sessions, and during yesterday revision session. Karthik had shared certain important things. So before doing that, let's go through the important parts of our syllabus. Am I audible? Can somebody give me a hands up? Yeah. Thanks, Kunal. Thank you so much. Okay, so we go through first of all week one and week two. So week one has got Markov inequality. So for Markov, we have to understand very important thing that it is only applicable only for non-negative random numbers. So for any non-negative random number and for a greater than 0, then the probability of x greater than equal to a is less than equal to expectation of x divided by a.
Sir, are you sharing?
Oh, I'm sorry, really. Yeah, share. Okay, so we will revise the only important concepts. We will not go through into detailed, proofs which professor has done during the classes. So just from the point of view of quiz 2. So Markov inequality is for a non-negative random number. Probability of x greater than equal to a is always less than equal to expectation of x divided by a. It is a loose bound. Now we come to Chebyshev's inequality. For Chebyshev's, it is applicable for any random variable, whether it is positive or negative. And for Chebyshev, we need finite variance, that we need the variance value. And it says probability of absolute of x minus expected of x greater than equal to k standard deviation is less than equal to 1 by k square. This is also written at many places as, you can write it as p of x minus ex greater than k is less than equal to variance divided by k square. So both are same, Chebyshev. Okay, it is stronger than Markov's inequality. Now we come to Hofferding's inequality. For Hofferding's, there are key requirements that we have got a data set of xi's, and each xi belongs to IID. And xi has also is bounded by a certain range of a and b. In that case, probability of x bar, where x bar is 1 by n summation of xi minus of expectation x greater than equal to t is always less than equal to e to power minus 2nt square divided by a minus b square. So in one of the GA, I think there was a question on the coin toss. So in the coin toss, it becomes 1 and 0. And we have to remember this formula, e to power 2 and t square divided by a minus b square. These are the three inequalities. Then next one is from probability. from the Venn diagram. Probability of A union B is always less than equal to probability of A plus probability of B. Then is if A implies B, it means probability of A is less than probability of B. A implies B, you can always figure it out that A is inside B. Then only A is implying B. So these are the five important things. Then we come to JL lemma. So JL lemma says that for any data set X, which is in D dimension, then there is always a function which converts these points from D dimension to K dimension such that the distance is preserved. So distance is preserved means fx minus fy square is less than equal to 1 plus epsilon x minus y square, and it is greater than 1 minus epsilon x minus y square. Now here important thing to remember from the quiz point of view is that k is O notation log n by epsilon square. It does not have any relation with dimension D. So in the PYQ, there is a question on this concept, and in the GA also there is a question on this concept. So please just get these concepts thorough.
Sorry to interrupt, sir.
Yeah.
So login, we have to use ln or login?
Use natural log.
Okay, okay.
Yeah. Anywhere log comes, please use natural log. In fact, professor has also used natural log while explaining all these log values. Okay. Then professor had covered that why there cannot be a simple transformation, why we cannot, convert. For example, we have got m into d, and we just multiply this with something d into k to get m into k. So here we got that the r square value which was coming rrt has to come identity, and r is in m into k into k into m, due to which we cannot, this is not possible, due to which we come to approximate isometry. In approximate isometry, how do we do that? What we do, we just multiply. I will just cover the steps here. So we have got a data set A, which is of dimension m into d. We have to convert it to matrix m into k such that the distance between the data points is preserved. So what do? We just multiply it by r by root k. K we find from the formula, k is O notation log of n by epsilon square. And when we multiply this, we get this. Here, the important part is that here the distance is approximately preserved, depending on your epsilon value. We can have the confidence interval that it can be preserved. Another point is that here this v which we get, if we call this as u and this is v, then expectation of v square is equal to u square. This please remember here. That's how your distances are preserved. Okay, so that was JL lemma. So just simply we are multiplying with the, and this r which is there, rij, this rij, they belong to your normal Gaussian distribution 0 to 1. Expectation of v, if we take every vector here, then expectation if we take, it will be 0. And expectation of v square is equal to u square here, if it is u1, u2, u3. So expectation is here. So that's how the distance is preserved. So that's about JL lemma. Now, here there are the proofs which are there, that how it comes to log of n and by epsilon square. So there's a long proof. Yes, you can go through this. Just give me a minute, please. Hello. हाँ Blinkit. Okay, okay. I understand. Just give me 30 seconds, please. Okay, sorry, I had a delivery. Okay. So there is a long proof why this case O notation log n by epsilon square. Just we have to remember this. So main key takeaways from week 1 to week 2 is Markov's, Chabyshev's, Hofferding's. This P A union B is less than P A plus P B. If A implies B, P A is probability of A is less than equal to probability of B. And then for J lemma, we carry out a transformation by multiplying by R by root K, and we get the J lemma, this bound. So there can be some questions we will see in the GA. There was a question. See, when we say from the right hand side, this part, it means the max of fx minus fy square is less than equal to min of x minus y square. When we take the left hand side, it means the min of fx minus fy square is greater than max of this value. And this max and min, if the question comes, you can do this by finding the eigenvalues of x minus y square, eigenvalues of this transformation, and then you can compute the those inequalities. So there is a question, we'll have a look on that. So now we come to the GA of week 2. So week 2 is x belongs to geometric. Recall that discrete random variable has the following probability mass function. This is for the geometric. Using Markov's inequality, obtain an upper bound that p is x then greater than equal to 2p. So from Markov, we know that p x greater than a is equal to expectation of x divided by a. So we put here. So now we have to find only expectation of this x. So x we have given, x is 1 minus p, x minus 1p. We know expectation of x is nothing but summation from 1 to infinity x into probability of x. Once we open this, we get, we can remember this, that for geometric, the expectation is 1 by p. And here only I will cover for Poisson, it is p. Okay. So putting these values, we get 1 by 2. Now, in the second question, they have given that, for instance, if p is equal to 0.2, evaluate the probability of probability of x greater than equal to 2 by p. And what is the absolute difference between this probability and the Markov upper bound? So see, for Markov, we had got 0.5, and for this 0.5, for if we put the value of p is equal to 0.2, which has been given in the question, then your probability, this value which is a, this comes out to 10. So this 10 is the upper bound for x. Now for this upper bound, now we will find for the geometric. So for the geometric progression, we know that it means that our first success has come after at least after 10 attempts. And the formula for that is 1 minus p, k minus 1. We get k is equal to 10. So probability of x greater than equal to 10 is nothing but 1 minus 0.2 power 9, which comes 0.134. Earlier we had got 0.5. So our difference is 0.5 minus 0.134. Any doubt in this question? Anybody? Okay.
This was quick. Okay.
Yeah. Yeah. So I will. So we have to remember here that for geometric progression, GP, probability that your has come after a times attempt, it is 1 minus p, that these many times I have not found success, and this is a minus 1. It means at 8th time I have got, and at a minus 1 times I had not got success. That's how this probability comes. Okay. So for other distributions, I also have mentioned, for example, Poisson distribution, most likely they will give, we don't have to remember. We just have to remember that expectation of x here is lambda. For this is the e power minus lambda and 2 lambda to power k. For exponential distribution, your expected x is 1 by lambda. So this we have to remember, 1 by lambda. For uniform, we know it is 1 by 2 p minus a. Now, the third question was if x belongs to normal 0, 1, using Chebyshev's inequality, we get the following bound. Probability of x greater than equal to -2 and less than equal to 2. And we have to find the value of this p. So remember this Chebyshev for a normal distribution, it just means that x is less than equal to 2 and -2. If we see a normal distribution, it is saying that here it is 2, here it is -2, and we have to find that x is between that. X is less than 2, so it will come here, and x is greater than -2. So this probability will be 1 minus probability of these regions. These regions we can find by using Chebyshev's. So we know for Chebyshev's p x minus x bar greater than equal to k into standard deviation is less than equal to 1 by k square. So we know standard deviation is 1 for normal distribution and mean is 0. So px greater than equal to 2 will be less than 1 by 4. So this region which has come, this both the regions, this is 1 by 4. So this region will become 1 minus 0.25, which is 0.75. And this will be the probability. This is less than, so here this probability will be greater than equal to 0.75. Is this clear? Any doubt in this? I can explain again. And if I'm not wrong, we had read, read this, I think during Maths 2 or Stats 2.
Yeah, this was in Stats 2.
Yeah. Okay. So now again, the question is, this is a tricky question. Normal 0 to 1, using Markov's inequality, we get a following bound. So this is x square greater than equal to 2 less than p. So we know this is directly Markov formula we put, ex square by 2, but we have been given only expected of x and we have been given variance of x. So here we have to find e of x square. So we will use the formula variance of x is equal to expected of x square minus ex whole square. So ex whole square will become 0. Variance is 1. So your expected x square will also become 1. So putting this value here, then we can find ex square greater than equal to 2 is less than 1 by 2. Fifth question is, again, x is in normal distribution with 0 and 1. The fourth moment they have given x, expected of x to power 4 is equal to 3. Using Chebyshev inequality, we have to find the bound x square greater than equal to 2 less than q. So remember the Chebyshev says absolute value of x minus ex greater than k standard deviation is less than k square, which also we can write as x minus ex greater than k is less than standard deviation by k square. So here we have to find probability of x square greater than equal to 2. So if we take y is equal to x square, so then we have to find e of y greater than equal to 2. Expected of y will become expectation of x square. It is a normal distribution, so expectation of x square is 1. Variance of, now here we will find, use this expected x4 which they have given in the question. So variance of y will become expectation of x to power 4 minus expectation of x square. So here we found 1, they have given in the question 3. So variance of y is 2. Now we put this in this formula. So we have found the variance k they have given. So we can write px square greater than equal to 2 as p of x square minus 1 greater than equal to 1. So we have taken 1. This 1 is expectation of x square greater than equal to 1. We put here, so standard deviation we put on top, niche k square, so we get value 2. So if you see this probability, probability has to be between 1 and 0. It is not matching, but for this question we found that it is coming less than equal to 2. Next question was the that it was a straight away question number 6. So you can see that all the points there in the same on the same line, and they can be easily transformed. So we don't require that isometry. They can be transformed by a normal linear transformation. Question number 7. A and B, they belong to R10. They are two random vectors whose entries are IDs, standard normal variables. C is equal to A minus B. Let T be the sum of all eigenvalues of the matrix CCT. Observe that T is a random variable. What is the expectation of T? So we have to remember this C. C is equal to A minus B. Both are normal, standard normal deviations variables. So expectation of C will become expectation of A minus expectation of B, which becomes 0 minus 0. And variance of C will become variance of A plus variance of B. We know this from our stats too. So this becomes 1 plus 1. So variance of C becomes 2. Now we use this for our variance. So variance of C is equal to expectation of Ci square minus expectation of Ci square. So here we get expectation of Ci square is equal to 2. So CCT, if we see, CCT is nothing but C1 squared, C1, C2, C1, C3 up to C1, C10. So these are the eigenvalues. We know that when we do AT, your diagonal elements which are there, if we sum them, then they are equal to sum of diagonal is equal to sum of eigenvalues. This we know. So we know that it will be expectation of C1 square plus expectation of C2 square up to C10 square. And we have found expectation of Ci square is equal to 2. So this will come 2 into 10, 20. We come to next question. Consider a training data set for multi-class classification problem which has got 1000 data points, n is equal to 1000, which has got 10 classes. So D is equal to 10 classes, where each class contributes at least one data point. Classes 1, 3, and 5 together contribute 200 data points. 2, 3, 4, 400 data points. A data point is picked up at random. P is the probability that it belongs to any of the following classes 1, 2, 3, 4, or 5. Find P. So we know that probability of 1, 2, 3, 4, 5 is equal to probability of 1, 3, 5 plus probability of 2, 3, 4 minus probability of 3. Probability of 1, 3, 5 they have given 200 by 1000, 2, 3, 4, 400 by 1000. Probability of 3 we don't know. But they have given that every class has got at least one data point. So probability of 1, 2, 3, 4, 5 is nothing but 0.6 minus probability of 3. Now 3 has at least one data point. Therefore, probability of 3 is greater than 1 by 1000. Probability of 3 is greater than 0.001. We put this 0.001 to find the probability. So it will become 0.6 minus 0.001. So probability of 1, 2, 3, 4, 5 has to be less than 0.599. As the data points for class 3 increase, this probability will decrease. So this was probability is less than 0.6. In next question, they had asked the same value, which we have calculated. Now they have given that across all possible data set that satisfy the conditions given the common data, what is the smallest possible value that P can assume? Your answer should be exact with 3 places. So see, for 135 we have got 200 points. So maximum of number of class 3 can be 198 only, because 1 and 5 they can have minimum only one data point. Similarly, in 2, 3, 4, maximum data points for 3 can be 198 here. So probability of 3 is 198 by 1000. This is the maximum probability of 3 that which we are getting from this data. We put this maximum probability of 3 in our earlier, and it becomes 0.6 minus 0.198, which becomes 0.402. So this is the smallest value for minimum P. Next question is a biased coin whose probability of landing heads equals P is tossed 10 times. Let Q be the probability that the fraction of heads observed is at least 0.1 plus P. So here it is a Hofferding's inequality they are asking. Using Hofferding's inequality, we get Q less than equal to R, enter the value of R correct to two places. So Hofferding says that it has to be in a range. So it is a coin toss, A is equal to 0, B is equal to 1, and they have given 10. This is the formula for Hofferding's probability of xi or x bar minus expected of x greater than equal to 2 is less than equal to e to power minus 2 nt square a minus b square, where x bar is nothing but your observed one, summation of xi divided by n. Expected of xi for a sum or for a coin toss is p. We know that. So we have to find probability of 0.1 plus p less than equal to r, because q they have given 0.1 plus p. So if we put in the Hofferding's formula, so it will become expectation is p, this is x bar greater than equal to t. So probability of x bar they have given is greater than 0.1 plus p. We can convert this x into probability of x bar. We bring p here greater than equal to 0.1. This will become less than equal to e to power minus 2. This is n, and this is your t square, and we get the value 0.818. So while solving these questions, maybe in quiz they might ask directly to use Hofferding's or Chebyshev's. But remember, Markov is a loose bound, Chebyshev is a tighter bound, and then Hofferding's we need certain conditions. We need range bound. So if those kind of things, then it can give us a cue what to use. Now, consider the same setup with two changes. The coin is now tossed n times. Q dash is the probability that the fraction of head observed is at least 0.01. So here they have changed the value of t, 0.01 plus p. Let the bound obtained from Hofferding be Q dash less than equal to R dash. What is the smallest value of n? That would guarantee that R dash is less than equal to e to power minus 0.2. So again, putting the same probability of x bar minus p greater than equal to 0.01 is nothing but x bar is greater than 0.01 plus p. They both are same notations. And this is less than equal to e to power minus 2n, and here t value has changed. So we get this value. Therefore, e to power minus 2n 0.001 square has to be less than e to power minus 0.2. We solve this and we get the value of n. We just remove exponential, we get the values. Next question is, consider an outlier detection algorithm that is deployed by a data science company. Assume that the number of outliers it detects on a given day is random variable with mean 50. So expectation of x is 50. Let p be the probability that number of outliers exceed 75. Choose the tightest bound with the information available at your disposal. So if we see here, we can use only Markov. And Markov, we know the formula, probability of x greater than equal to a is less than expectation of x by a. And we also know for the Chebyshev, x minus x bar greater than equal to k is less than equal to variance square by k square. So, but for this we need variance. Variance is not given in the question. So we use Markov, and straight away it comes 50 by 75. So this was an easy question. Next question is, the variance of the number of outliers is equal to 25. So once the variance is given, then we can use Chebyshev because it will give tighter bound. Let Q be the probability that the number of outliers lies between 40 and 60, and points included. Choose the tightest bound with the information available at your disposal. So always, try to visualize these problems. So they are asking that value is between 40 and 60, endpoints are available, mean is 50. So by using the Chebyshev, we can get this information, this probability, and then subtracting from 1, we can get the this probability. So straight away we put in the formula Px minus 50 greater than or equal to 10, because 40 and 60, they are at a distance of 10 from mean. So that will become 25 by 100. They have given variance 25, 0.25. Now probability of this one will become 1 minus 0.25. This is the bound. Next question is, let R be a 100 into 10,000 random matrix whose entries are IIT standard normal. M is equal to R by 10. This is the, we can see this is the root K into U. It belongs to R 10,000. Is a non-zero fixed vector, and V is equal to MU, which is of the following is true. So expectation of V square is equal to U square. That is the correct one. M is equal to R by root K. You can find here that expectation of V square is equal to U square when you are using the normal random variables. This is the basic core of JL lemma. JL lemma. Okay. Now they have asked X is equal to 10 into V divided by U, then which of the following is true? So here they are asking the value of basically expectation of X square. So expectation of X square is nothing, you put the values. This will become 10 V whole square by U square. 10 becomes 100. This becomes V square expectation. Expectation goes inside. And we know expectation of V square is U square. U square cancel. So expectation is 100. So expectation is, and professor had explained also. And if you go to the notes, you will find if you put the value of X is like this, then expectation of X is nothing but it comes K. Now, next question is, consider a data set D of n data points in RD. Given epsilon less than 1, greater than 0, let F be a linear map from RD to RK. An approximate isometry is guaranteed by JL lemma. Which of the following are true? So these are straight away from the JL lemma definitions, that F of 0 is equal to 0. F of x plus y is equal to fx plus fy for all xy in RD. And this is the standard definition of JL lemma. So these three things we can remember for JL lemma. Okay, next point, question. Consider a data set D of n data points for a binary classification problem in RD that is non-linearly separable with spherical decision boundary. To be more precise, the set D plus of all positive data points belongs to region x square less than equal to R1 square. And the D minus of all negative data points belongs to the region x square greater than R2 square, with R2 greater than R1. To get a visual picture, think about D is equal to 3 and consider two concentric spheres. So just think basically from in a 2D, so these are all points. This is R1, and here all are positive points. This is R2, and beyond this, all are negative points. So this is how, with the available information, which of the following statements is true concerning the positive data points in RK after the transformation? The norms are with respect to RK. So this we can take directly from JL lemma, that fx square, if you see fx square is less than R1 square, there is nothing in JL lemma like this. Fx square is less than 1 minus epsilon. This is wrong. This is greater than equal to. Fx square is greater than equal to 1 plus epsilon. That is also wrong. It is less than equal to. So we come to last one, which is the correct one, that fx square is less than equal to 1 plus epsilon into R1 square. That is the correct one. If R1 over R2 is 0.2, find an upper bound for epsilon that ensures that the data set continues to be spherically separable in the lower dimension. So see what it is meaning, that fx square is less than equal to 1 plus epsilon x square for x points, and similarly for fy, we put JL lemma. Now, maximum of fx square has to be lower than fy square. So maximum of this has to be lower than of fy square for spherically separable. So it means 1 plus epsilon r1 square has to be less than equal to 1 minus epsilon r2 square. R1 over R2, they have given 0.2. We solve this and we get the answer, which comes around 0.992. So with this, I have covered week 1 and week 2. Any question, any discussion, anybody wants to contribute? Okay, no problem. So shall we go to week 3 and week 4? Okay, good. So now we come to week 3 and week 4. So in week 3 and week 4, there are two different concepts which have been covered. So the week 3 is a continuation from week 1 and week 2. Basically, that if we have got a data set which has got, n is very, very large. So by using JL lemma, we cannot, do the calculations because it becomes computationally expensive. So week 1, week 2, we realized that we can transform data from D dimension to K dimension with reasonable assurance of distance preservation. However, if n is very high, then a new query will take, first we will have to convert the query from D dimension to K dimension, which will take O and dk for n points. Then the query vector we have to convert from D to K, which will take O dk. And then we have to compare with n points, which will take O and k. So if n is very, very high, then this third part becomes very, very computationally expensive. So for that, the solution is the local sensitive tree hashing. That we have got a hashing function by which we put all the data points in buckets. And when some query comes, that query will also land in that bucket. So that bucket has got less data points. And there now it can do, that nearest search, that which are the good points. So how to do that? Then that a family of hash function X is called RCP1P2 sensitive. This we have to remember from the quiz point of view. So there is R is greater than 0. Then we have got C is greater than 1, and P1 and P2 are the probabilities. P1 is greater than P2. It has got two main points. One is that X minus Y is less than equal to R, means the probability of Fx minus Fy is Fx is equal to Fy. Sorry, here there's a typo. Fx is equal to Fy is greater than equal to P1. And X minus Y greater than equal to CR, it means probability of Fx is equal to Fy is less than equal to P2. So any function which fulfills these conditions can be called a suitable hash function for LSH. And how do we do LSH, for example, for a Euclidean distance? We just convert, for example, this is the family of hash functions. HABX is equal to floor of A transpose X plus B divided by W. This W is the width of the bucket, which has to be greater than equal to 0. B comes from uniform from 0 to width of the bucket. A comes from normal distribution 0 to 1. So for all the points when we do, we can find all the points in the buckets. They will land in these buckets. Now the concept of the collision comes that when Hx is equal to Hy. So if we have to find that we have done this Hx, we find that 2 points, they land in the same bucket. So what is the probability? So probability of Hx is equal to Hy is nothing. Now if we see H, it is consisting of this normal distribution. It has also got the uniform distribution. So first, what do? We find only by fixing a particular A, we find for PB. So P probability of Hx is equal to Hy, we can break down into probability of A belonging to N0 I, probability of B, which is 0 to W, and Hx is equal to Hy. We fix A, given A, so this will become probability of B, Hx is equal to Hy. We put the values of Hx and Hy, Atx plus B by W is equal to Aty plus B. Now we define U is equal to Atx, V is equal to Aty. So we can find that U is nothing but U is equal to V plus delta, where delta is equal to U minus V. And probability will become floor of V plus delta plus B by W is equal to V plus B by W. Now, if we see this visually, it means that we have got width, these are the buckets, we have got V somewhere, then we have got V plus B somewhere, and for W, for the collision to happen, this is a very, very important condition, that delta has to be less than width of the bucket. So please remember this concept, this might come. Now, also remember, it has not been covered in the lecture. This is a necessary condition, but it does not mean that for any delta less than W, your collision will happen. It is only the necessary condition that for collision to happen, delta has to be less than W. And I have given one example in the notes where it is there, but the collision does not happen. So for collision to happen, take place, your B has to be uniform between 0 and W minus delta. This is an important condition. So we had started B is uniform 0 to W, but here when we fix an A, we find that this W delta is nothing V minus U minus V. Okay, so for collision to happen, B has to be uniform between 0 and W minus delta. So takeaways are there that probability of B for a given A, Hx is equal to Hy, is 1 minus delta by W when delta is less than W, and 0 otherwise. Now, if you take this delta was nothing but U minus V, and you do the calculations, you do the expansions, so you find that this probability which is there, it is a monotonically decreasing. It means when X minus Y is increasing, the probability decreases, and when X minus Y decrease, the probability of collision increases. So that's how this hash function ensures that collision probability which is there along with the distance. Now, what is the problem in LSH? So, and how to solve it? So if we take R is equal to 1, C is equal to 2, and we get P1 is equal to 0.8 and P2 is equal to 0.4. And for example, if the number of data points are 10,000, then for any query, the good points will be, for example, there are 10 and there are bad points which are 8,000. For example, there are good points inside which are close. So there are 10 and 8,000. So this is just an example, just to prove the problem in the LSH. Now, the hash function is 1 to 0.0.4. It means that probability 1, probability 2, for 10 good points, it is likely that 8 points will be in that bucket. So total points found in that bucket will be 8. But for P2, there are 8,000 bad points. So 8,000 into 0.4, then the total bad points will be 3,200. So this is a big problem, that your true probability rate is around 8. We have got 8 good points, but we have found 3,200 bad points. So now to solve this, we have to lower the false positive rate. So how to solve this? That we make a family of hash functions, and we say that every hash function will have to collide, then only it will be a good point. So here we are using AND, that all hash functions, for all hash functions, the query has to collide with that point. Now, new points will collide only if this, for example, this is the hash h1q is equal to h2q is equal to hkq, then only. And the false positive rate, in this case, it will become n into p2, the probability of bad point, into k, because it is and for all. So for pt is equal to 0.4, as k increases, FPR decreases. So from here, from this np to k, your main derivation
Excuse me,
comes.
sir. So why there is n in the false positive rate? Is it expectation?
It is not expectation. It is the number of bad points. It is the number of bad points which it will get.
Okay.
Okay. Because see, there are k hash functions. For every hash function, they have to collide. Then only the collision will happen. This is and. So for the bad, it will become p2 into k for every point. Okay, this is the number n into. And from here, when the derivation takes place, you get k is equal to log of n divided by log of 1 by p2. Please remember this. So when you fix this k with this value, k is equal to log n by log 1 by p2, then you sort out the problem of your FPR. Okay, then your FPR, for example, by selecting k, you can put these values in the same example which has been given, and you will find that FPR becomes 1. Now you can put this np2k is FPR is equal to 1, and then you get the value of k. Now here, but we have solved the problem of FPR, but your TPR will also become np1k, number of your good points. So this will also suffer. So by doing this k, you find that your TPR has also reduced to only 1. So you will get 1 good point and 1 bad point, whereas we want good points more in this bucket. So for this, what we do? Yes, somebody raised a point.
Yes, sir.
Yes.
So that TPR calculation,
Yeah.
can you show the pages?
Yes.
Yeah, this 10,000 into 0.8 to the power log of 10,000 by log of 1 by 0.4.
Yes.
When calculating it is not coming to 1. It is coming to some 1072. So is that calculation correct?
No,
And
no.
just wanted to know in the FPR part also you have put this equal to 1. So can you explain what is that?
It just said that for our example, if we had this k value, the k value which was there, k value comes around 10. Okay, just you can just remove this. Okay, the k value which comes for 10, and for 10 k value, now you find the number of this. So this will become 10,000 into 0.4 to power k 10. Okay, and find this value. So your number of points which will be there, it will come approximately around 10.
Okay.
Okay. So you have reduced your FPR, but your TPR has also been reduced by this AND function. Okay. Here, another important point I will cover, which has not been covered in the lectures. As k increases, your TPR and FPR both decrease. Okay. Because your TPR and FPR is nothing but P1 by K, where P1 and P2K. So as K increases and it is in decimals, so this total value which is there, it will decrease. Is that okay?
Yes.
Okay, so remember this, it might help. So now to how to solve this. So for solving this, what we do, we make tables. So we have got these tables where we have got this and that for this, they have to match. And out of these tables, for any table, if it matches, any means that here it is or and here it is and. So for anyone it matches, the collision will take place. Now for here, if we take for or, then your TPR will become 1 minus TPR will become that, for example, the collision has not taken place. So it becomes 1 minus P1K, that these are the K values, K. And how many tables are there? L. 1 minus this, the probability has not taken place, is 1 minus e to power minus theta. Here this you can write down this theta value which comes, theta comes from formula L is equal to theta n to power rho, where rho is equal to log of 1 by P1 divided by log of 1 by P2. Okay, so this theta will dictate your value of L, that how many tables you have. And here I will cover that as L increases, your TPR and FPR increase, because as you increase the number of tables, your probability of collision will increase, whether between good points or the bad points. So more the number of tables, the more the TPR and FPR. So remember this formula, TPR is 1 minus e to power minus theta, and FPR is nothing but theta to power n to power rho. And this rho is log 1 by P1 by log 1 by P2. These are the important parts. So what are the main takeaways? That for LSH, for first we sort out K. K is equal to log of n divided by log of 1 by P2. By this we have reduced FPR, but your TPR also decreases. Now to solve this, now what you do, you find a number of tables which is equal to theta n to power rho. Rho is equal to log 1 by P1 and log 1 by P2. Now based on your theta value, you can select the number of tables. And in this case, when you select, then your TPR becomes 1 minus e to power minus theta. And FPR is nothing but theta to power n to power rho.
Sir, is the value of L and FPR are the same?
L and FPR.
Yes, sir.
L and FPR, yes. If you see the formula, it is same.
Yes, sir.
Okay. Yeah. So you can put down these values in your the example, and we can find that good points, they have come to around 9. From earlier we were getting 8, now we are getting 9, and bad points have come down from 3,200 to 18. So now we can do the nearest search or KNN to find that. So this was week 3. So week 3 was continuation of week 1, week 2, and from JLemma we came down to LSH. So any question in LSH conceptually or anything? Anyone wants me to cover it again? Okay. So if there is no point, then I'll go to the next concept. So next concept is basically how to do SVD efficiently. We know from our stats 2, or I think from our MLF or MLT, SVD is breaking down a matrix of A, M into D, in M into M. This is your matrix with your eigenvalues M into D, and V transpose D into D. The complexity of this is M D square when M is greater than D. So if your M is very large and your D is very large, when you have more number of columns, then it becomes computationally expensive. So how to solve this? So there are 2 ways of solving this. One is that we know that A is equal to U sigma V. If it is the summation of Ui sigma Vi transpose. So by taking the vectors corresponding to your eigenvalues in decreasing order, you can get an approximation. You can get V is equal to UK sigma V A A to D. So by taking this, you can get the best approximation of the that matrix. But we have got another method which is known as fast SVD, and in fast SVD we use this randomization. So I will go to the fast SVD. Only one thing we have to remember, that when we do, for example, this, if we are selecting the first top eigenvalues, and then if we calculate A minus B, then it will always be equal to eigenvalue, which is the left one. So we have selected kth eigenvalues to calculate B. Then the difference between A and B will be the eigenvalue next. And this question is there in the GA also, and it is there in the PYQ also. So this is from approximation. Now we come to fast SVD. So for fast SVD, what do we do? I'll just cover the important parts. What we do, we have find a matrix which is of the order, which has got all the vectors which has belong to values normal Gaussian distribution 0 and 1. So this is W1, W2, WL. And this L which is there, L is equal to K plus P. K we need, and we add some number P for generalization. So we have got this matrix omega W1 to WL. Second step we do, Y is equal to A omega. So A is equal to M into D, and we do omega, which is D into L, and it will give me M into L. So this Y is equal to M omega, M into D, M into L. Sorry, this is a typo. And complexity is ML. Now, expectation, remember, this is very, very similar to our JL lemma. In JL lemma also, we were multiplying a matrix with a normal distribution. So expectation of this A omega is 0, whereas covariance of this O omega is A into AT. We find basis of this Y is equal to A omega. This will be, complexity will be ML square. We find Z is equal to QTA, transpose of this QTA. Again, complexity will be MDL, output will be L into D. And now we do SVD of this Z. So here we have got LD, complexity we have reduced to DL square. Once we do SVD of this Z, now we find the SVD of A is equal to Q into this U, which we have got from here, U delta, sigma delta, V transpose delta. So we multiply Q into U, we retain this top K eigenvectors from here and V. So by this, we have reduced the complexity from MD square to OMDL. So I will cover here again. So what do we do? Steps. A is equal to M into D. We find omega is equal to D into L with all values omega ij belonging to normal distribution 0 to 1. T, we do Y is equal to A omega, which will give us M into L. And complexities we can write down here to form this omega will be ODL. This will be OMDL. And this Y omega which is there, now expectation of all the vectors of this I, remember expectation of Y is equal to 0, and covariance of this Y will be equal to A into A transpose. Now fourth we find Q is equal to orthogonal basis of Y. Now this is ml. For orthogonal, the complexity is OML square. For this cube, now we find Z is equal to Q transpose A. This Q transpose A, so this is Q is again ML, M into L. So this will become L into M into M into D. So this will be L into D. Now sixth is we do SVD of Z, which will give us U tilde summation tilde V transpose tilde. So these are the SVDs of Z. From here now we retain, now we do SVD of A is equal to Q into U tilde, this one. We retain top K values from here, sigma K into K, and V transpose T. So this is how we get an efficient SVD of A in MDL. Is this okay? All these steps with everyone?
Yes.
Okay, very nice. Now here another concept which is there, that what will be the difference between Q and UK? So just remember these formulas. QQT minus UUT will be less than your eigenvalue K plus 1 for A divided by eigenvalue Kth eigenvalue. So this is the difference. There is also another thing, that if we keep on multiplying this AA transpose Q times with A, this difference will keep on decreasing. And this can be written as A transpose QA is equal to this UVT remains same, only this eigenvalues which are there, this remains 2Q plus 1. And if you put this in this formula, then your difference will become K plus 1 eigenvalue divided by Kth eigenvalue power 2Q plus 1. Now to utilize this, I will cover it later. The iterative, how do we do using the iteration? So now we come to the GS for this part. Which are the following represent the time complexity of n data points in RD to RK? So this is nothing, n into D into D into K. We know complexity is n into D into K. It is easy. A family of hash function is called R1, C1, P1, P2 for these values. So this is straight away from the definition of your hash function for LSH. So this we have to remember. Then again here RC, P1, P2, they have given the values. They have given XY belonging to RD. 2 points such that X minus Y is less than 1. The probability that both these points are hashed to the same value by a hash function sampled from this family is at least P. Enter the value of P. So see here, this is R, this is X minus V. Probability that these are to the same value by a hash function, that X is equal to Y. So this will be equal to your P1. Consider a data set in...
Can you explain that one more time, why it is P1?
P1 because straight away from the definition. From definition it says, what it says, if X minus Y, less than equal to R, it means probability of X is equal to Y is greater than equal to probability 1. So here, if you see, X minus Y is R value is 1. So they're asking the probability that both these points are hashed to the same value by a hash function, Hx is equal to Hy. Hash function is at least P. At least P means P1. Is that okay?
Yeah.
Okay. Consider a data set in R4 where each data point lies on a line passing through the origin, which is represented by a unit vector. Also, all points in the data set are at a distance of most 2 units from the origin. Next, consider the hash family, hash W is equal to 2, HAB standard definition. B belongs to 0 to 2, W, with A normal 0 to 1, B is uniform 0 to 2. Let hash function be a function that belongs to this family. Note that here H is not a random function. Specifically, B is equal to 0 and A is a vector that satisfies A transpose U is equal to 2. Now consider the set S is equal to Hx, X belongs to D. Find the maximum number of elements in S, that is find an upper bound for S. So here they have given B is equal to 0, ATX is equal to 2, W is equal to 2, and every point xi is equal to alpha u because all are passing through the unit vector. All points are passing to the line through the origin represented by a unit vector. So we can write every data point is equal to alpha into this u. Also, all the data points are at most 2 units. So your xi is less than equal to 2. So if you put here this xi is less than 2, so your alpha, this u is unit vector 1. So your this alpha is also absolute value takes less than equal to 2. So alpha it can take values only -2, -1, 0, 1, 2. Now we take hash function. Hash is equal to ATX plus B by W. B is 0. X we put alpha u. Alpha comes outside. ATU, which is A to U, they have given AT is 2. 2 cancel out, and we get function of floor of alpha. Now we know alpha can take only this -2, -1, 0, 1, 2. So we will have 5 buckets. -2, -1, 0, 1, 2. Is that okay?
Can you repeat that one more time?
Okay. So see, from here we have taken from each data point lies on a line passing through the origin, which is represented by a unit vector. So every data point I can write down alpha into unit vector, number 1. Number
Yes.
2, all the data points, they are at most 2 units. It means your x, which is there, it is less than equal to 2.
Yeah.
Okay. So this, if I can write down this xi, which is there, it can be written as alpha u is less than equal to 2. This is unit vector. So alpha is less than equal to 2. Absolute value of alpha. So if alpha is less than equal to 2, alpha can take values. How many values? 0, +1, -1, +2, -2. These are the
Yes.
values. Now, when we take the hash function is equal to ATX plus B by W, floor value. B is 0. X I can write down as alpha u. It becomes alpha into ATU by 2. ATU, it has given 2 for all. ATU is 2 from here. So this will take all the values, the hash can take all the values of alpha. And how many alphas we have got? We have got 5. 0, 1, 1, 2, 2. Okay?
Yeah.
Okay. Now we go to next question. Consider the hash. Again, hash is there. We define specifically this. For H1, we have got A is equal to 1, 0, B is equal to 0. For next hash function, we have got A is equal to 0, 1, B is equal to 0. Now, X belongs to R2 is some fixed point. A point Y belonging to R2 collides with X if Gx is equal to Gy. If S is the set of all points that collide with X, find the area of S. So see, for hash function H1, W is equal to 1, A is equal to 1, 0, B is equal to 0. For hash function 2, W is equal to 1, A is equal to 0, 1, B is equal to 0. So let's take that your point X, which is there, it is X1 and X2. Okay. Now hash 1 of AB will be 1, 0 into Y1, Y2. A is 1, 0. If you multiply this, you get Y1. Now for collision, it means your Y1 has to be equal to X1. Then only collision will take place. Similarly, for your next hash function, it becomes 0, 1, y1, y2. From here, you get y2. So your y2 has to be equal to x2, then only the collision will take place. So for both hash functions, if they have to collide, your h1x is equal to h1y, y1 floor which is there equal to y2 floor. Then only that you take the floor value of this, then only the collision will take place. Now for this collision to take place and your width which is there from here, the bucket width is w is equal to 1. So your y which is there, y1 can go maximum up to x1 plus 1 and your y2 can go maximum up to x2 plus 2 if the collision is taking place. Otherwise the collision will not take place. Now when you plot it, x1 plus 1 and x2 plus 1, so this is the area and area will become 1. Is this okay?
Yes.
Okay. Okay, here only this part was confusing. I will remove this. Okay. So here I will write, for example, if this is the floor y1, it means y1 has to be maximum to x1 plus 1. For y2, again the floor y2, the y2 can take maximum x2 plus 1 for collision. Okay, and then we can find the area. That is fine. Okay. Next question is there. H W is equal to 1, R C P1 P2 sensitive hash function. We construct a new hash family G lambda using H1 where every element Gi is from dimension 3 to 7, and this is the you have got 7 S functions. So they have given H1 7. So there are S functions. Suppose Gx is equal to H1x, H7x, which is G lambda. We define collision where Hy A is equal to Hyb more than lambda. So evaluate the true positive rate for the family G lambda is equal to 1. So we have to understand what basically it is talking. G lambda is equal to 1, it is saying from here that out of 7 hash functions, even for G lambda 1, that at least for 1 there should be a collision. So it can be 1, 2, 3, 4, 5, 6 and 7. So at least for 1 collision takes place and it will say that the collision has happened because here they have defined it like so. So this is nothing. TPR lambda is equal to 1. It means that no collision has taken place and we subtract that from 1. So no collision will take place. It means your 1 minus P1 is the probability of collision. Collision has not taken place, so 1 minus P1 to power 7, which is the value of K, and we subtract from 1, so we get the TPR. Is this okay?
Sir, I have a doubt here. Sir,
Yeah.
in the formula, it is 1 minus P1 to the power K and raised to power 7, whole raised to power like L. So,
See, so here the tables are not there. Here it is only one family is there. Okay.
so sir, if it is K, then it should be inside the bracket, no? Like,
See, I'll just tell you. Okay, just a second. These are H7X, okay? So your collision has not taken place. It is asking TPR for G lambda is equal to 1. It means for at least 1 collision has taken place. So it can take place for 1 also, 2 also, 3 also, 4 also, 5 also, 6 also, 7 also. So we have to consider all cases. And that is nothing but 1 minus no collision, that no collision had taken place. So if the no collision had taken place, So for this also collision has not taken place. So this is P1. For this also 1 minus P1, sorry. For this also collision has not taken place. So 1 minus P1. So this has happening how many times? 7 times. So this is equal to 1 minus P1, 7.
Okay, sir. Got it, sir.
Okay. Yeah. Okay. Now evaluate the false positive rate for the family G lambda is equal to 1. False positive rate means the collision has taken place with the bad elements. So for the bad elements, we take P2 and use the same formula. Okay. Now evaluate the true positive rate for the family G lambda is equal to 5. G lambda is equal to 5 means now we will consider 5 also, 6 also, 7 also. That at least 5 has taken place. So for 5 collisions, TPR will be equal to probability of 5 plus probability of 6 plus probability of 7. And this is a binomial. So for probability of 5, it will become 7 choose 5, probability 5, 1 minus P2, which comes this. P6, 7 choose 6, P6, 1 minus P, calculate and add it up and it comes.
So how do we know that it is a binomial? Is it mentioned somewhere?
See, either collision is taking place or no collision is taking place.
Okay.
Okay. So when there is a binary kind of thing, and then we have got continuous that I will not stop till the time I get, so it becomes a binomial distribution. Like for example, you keep on tossing your coin, and you got 10 tosses, and you say that I will not stop till the time I get a head. So it is a binomial distribution. Okay.
Okay, sir.
Okay. Evaluate the false positive rate for G lambda is equal to 5. So again, the same concept, it will come. Which among the following families has the highest separation between the true TPR and FPR? So this is very lengthy that you have to calculate TPR and FPR for all. So I just wrote a Python code and I solved using Python. So initially, it increased and then it decreased. So for G lambda is equal to 5 was the correct answer. I hope this kind of question will not come. Okay. Next question is let's XP. Now from here the SPD concept has come. This was till LSH. Let X be a matrix of shape n into D. If n is greater than D, which of the following represent the time complexity? So remember, time complexity of SPD is OMD square if m is greater than D, or OM square D if m is less than D. Consider the matrix A given below. How many non-zero singular values does the matrix have? So for this, please find the rank of the matrix. So see, 1, 2, 3, these are all zeros. So rank of the matrix is 3. So you'll have 3 non-zero singular values. Find the sum of the non-zero singular values. So for this, we have to calculate the singular values. How do we do that? First, we do the A, for example, I have removed this 0 values. I have found A dash, and then I found A dash transpose. Then we multiply AAT. This is the standard method of finding the eigenvalues. And now from here you find the eigenvalues. So straight away you can check here that lambda 1, lambda 2, lambda 3. So your eigenvalues are 25, 16, and 9. And non-singular values which are there, remember, singular value is equal to square root of your eigenvalue. So this will become 5, 4, and 3. So please remember this in the quiz if the question comes. Now choose the best rank 2 approximation of A. So now what we have done, we have found the non-singular values. So best approximation, we know that it will always be from the highest to lowest. So we have found 25, 16, 9, non-singular values 5, 4, 3. So your best 2 rank of 2 will contain these values 5 and 4. So whichever matrix has got 5 and 4, that will be the best approximation. Next question is, consider a survey in which 100 people are asked to rate 100 movies. The rating scale is from 0 to 100. The data is gathered into a matrix M. It is observed that 50 people have given identical ratings for all the 100 movies. If X and Y are the rating vectors of these 50 people, then Xi is equal to Yi for all movies. Now, M can be decomposed as a product of two matrices B and C. We know that it can be done because 100 into 100 can be broken down into 100 into 5 into 5 into 100, and we will get that. So this is a correct answer. Second is, M can be decomposed as a product of two matrices B and C, each of rank K, such that K is less than or equal to 51. So see, this 51 figure is coming from here, that we have got 100 into 100, but 100 people have given similar, everything same. So these are 50, these are 50 same. So these can be converted into a single row. 1. So this can easily be converted into a K which is less than or equal to 51. So both are true. Let A be a matrix whose non-zero singular values are this. If B is the best rank 3 approximation, then compute A minus B. So A minus B is always equal to your singular value or K plus 1 singular value. So K is 3, find the fourth. So 1, 2, 3, and 4. So this will be your answer. Consider an n into D matrix A, let UK be into n into K matrix whose columns are the first K left singular vectors of A. Then UKT is the best rank K approximation of A. So you have taken or the first K left singular vectors of A. It means your UK which is there, it is the best rank K approximation of K. Always remember, it is the projection of the columns of A into the first K left singular vectors, not on the rows. It is the projection of the columns of A. This is directly from, if you read SVD, just go through the standard steps, know the meaning of that. Then they have given A, consider a random vector W, find the covariance matrix of A, AW. So from here, we had known that if you multiply a matrix into a matrix which has got only normal distribution, then this is A, this is omega. The covariance of A omega is nothing, is equal to covariance of A into AT, or sorry, A into AT. This you remember. So find the A transpose, multiply by A, and you will get the answer. Next is AB, ND matrix of rank R, whose SVD is given as A U sigma VT. Let omega is W1 WK. So here they have given A omega. This is normal distribution. The columns of A omega will span the column space of A. This is wrong. A omega, the span of columns will be in the subspace of column A. They will not span the column space of A. The span of first K left singular vectors is subspace of the column space of A. So the left singular vectors which will be there and A which is there, it will take the first K left singular vectors which are there. It will take those places. It will leave out this.
So what if in the previous question, what if the omega matrix is still the m dimensions, m cross t dimensions, like it is fully the K matrix is full. So then in that case, is it column space or subspace?
Okay, so you are trying to say, for example, A is equal to m into D, and now we have got omega, which is D into D. You are trying to say this, and it has got all. Now, for example, omega ij is equal to belongs to n 0 1. Is that okay? You're trying to say this?
Yes, sir.
Yes. Then it will have your full column space which is there, It will have the entire space of A. Okay. If it is only having, for example, D into K, it will have only the span of the first K. Okay. Is that okay?
Yes.
Okay. Okay. So can we move to week 5 and week 6? That I will cover slightly fast because with, yeah, okay. Thank you. Okay. So with that, we go to week 5 and week 6. Week 5 and week 6, basically it starts with the limitation of K nearest neighbor, that KNN, KNN always depends on the Bernoulli regions, that there are definite boundaries between the regions, then only it can differentiate. But however, if we have got some regions like this, then we cannot differentiate. So for that, answer is the spectral clustering. And spectral clustering is basically, so I will cover not the cuts and all that. I will not go into that. Basically, we have got points and we find the cuts which minimizes the Wij. Wij is equal to e to power minus 2x minus y square divided by hyperparameter. I think some sigma square is there, which is hyperparameter. So more the distance, less the Wij, less the distance, higher the Wij. And when we take a cut means that your summation Wij and you are doing Fi minus Fj. So if they belong to different buckets, 0 and 1, and you do the square. And when you do the summation, it comes out that it is a Laplacian, and Laplacian is nothing but d minus w. So this is equal to summation of Wij Fi minus Fj square. So to find the solution of this, you just take the eigenvector corresponding to the second smallest eigenvalue, which will correspond to the mapping of all these points into a linear space. And then we can carry out a KNN on this. So this is the basic crux of your week 5 and week 6. I will cover certain points during the GAs, how to solve that. Because during the revision session also, Karthik had mentioned that try to attempt J-lemma questions first and the spectral first, because I think they will be based on the calculations. And then we go to the conceptual of the SVD and LSHA. So straight away, any question, any discussion on Laplacian, if anybody wants to have. I'll cover just certain parts of Laplacian. Okay. Here. Okay, what is a Laplacian? So we have got, for example, 3 points. First, we make the adjacency matrix. We call it as a W. It is nothing but, for example, x1, x2, x3, x4, x1, x2, x3, x4. So this is 0, 0, 0, 0. And these are the distances, the W's which are there. For example, 1, 1, 2, 1, 2, 1. Three is 3, 1. So this is W, and then you make something called degree matrix. Degree matrix, which is D. D is nothing but summation of all the, so for x1, summation of all the distances, so it becomes 4, rest all are 0. x2, summation of all this becomes 4, 0, 0. x3, 0, 0, again it is 5. And x4, this is 0, 0, 0, 4. And when you do the Laplacian, Laplacian is nothing d minus w. So this Laplacian has got certain qualities we can see in this example. This will become 4 minus 1 minus 1 minus 2. 0, sorry, minus 1 4 minus 3 minus 1. So this x2 was 5. Sorry, my bad. This will become minus 1 minus 3 5 0 minus 2 minus 1 minus 1 and 4. Now see, there are some quality of this Laplacian. First of all, the sum of every row is 0. So when the sum of every row is 0, it means it will have at least one eigenvalue is equal to 0. And this eigenvalue which has got 0, the eigenvector corresponding to this, will have all ones. It will have all ones. So this is first property. Now it is an eigenvalue is equal to 0. And if you see, it is a symmetrical matrix. The property of this is that if you take any x and L, xt, L, x, it will always be greater than equal to 0. Why? Because this xt, Lx is equal to summation of wij fi minus fj square. All the weights are positive. This is a square, so this is a positive quantity. So this is always greater than equal to 0. Therefore, it is a positive semi-definite matrix. Definite matrix. It is not definite matrix because one eigenvalue is equal to 0. So these are the properties of Laplacian. And when you find the eigenvalues for this Laplacian, now we know that one eigenvalue is 0. So next smallest eigenvalue which is there, that will correspond to the mapping of these data points to your linear space, and we can carry out KNN on that. So these are the properties. So with that, we just come to the GAs. So for the GAs, ABC means just A, B, C, and in the second part is ED. So we find the distances from A to E, A to D, B to E, B to D, C to E, C to D. So by that you compare the distances, and the cut which will give the less cumulative weight, it is the best cut. So that was the question. This question 3 is all about, just now I covered important concepts. I have covered adjacency matrix, degree matrix, Laplacian, properties of Laplacian. Please go through the properties of Laplacian. It might come in some form or other. And the determinant of this Laplacian L is 0, and that's why it is not invertible. This is the how we arrive at this function. Basically, the cost function is this: half wij fi minus fj square. When we expand it, we find this wij fi square is nothing, fi square w sigma f wij. Sigma wij is nothing but it is a degree matrix which we have found. Minus 2 wij fi fj is nothing but minus 2 ft w, which is the first matrix, adjacency matrix, and this third is the ftdf. We calculate, then it becomes f dash d minus wf. This is the approximation of the cost function. Okay, what I suspect that there will be a question on calculations of this. So these are the calculations. Straight away mathematical calculations are there. There are no twists. So just remember the steps. First you have to make the adjacency matrix W, then make the degree matrix. From degree matrix make the Laplacian. From Laplacian now find the Laplacian. What you can do, you can use this row property. So we can do the matrix manipulation to get zeros, and then we can easily find the eigenvalues. And then the eigenvalues, the second eigenvalue which is there, from that we can easily find the eigenvector. Okay, so that straight away they are all theoretical questions which are there. So this one question is there which Karthik had covered during the revision. So on this concept it might come. So this is about that when we make, for example, we have done the spectral clustering, but the problem is that your Laplacian is a dense matrix. So to make this dense matrix into a sparse matrix, we do something, we remove some edges. So for example, if there is a point and there are edges 1, 2, 1 and 2. So what do? We remove some edges with the probability. We keep only one edge. We keep only one edge. And this is your LH, Laplacian with the transformation. So this is a formula which is there, that when you do find the distance, this FT, LH, F, it will always be less than equal to 1 plus epsilon with original. So try to correlate with your JL lemma, and greater than equal to 1 minus epsilon. He had said they will not be asking question on this, and they might ask question on this. F, what is the notation? So complexity, F is O V log V by epsilon square. So with this, friends, I have finished. If you have got any doubt in P by Q, we can discuss if you have done that. Any question in Laplacian or any conceptual? So we have seen, I will start from the beginning. We have started from Markov, Chebyshev's, Hofferding's. Then we went through the JL lemma basics. How do we do the JL lemma? Then we came to that although we have reduced the dimensionality, but if the data set is large, then we will face that problem. So from that, the local sensitivity hashing came. So, and in the local sensitivity hashing, we saw an example that TPR, how the FPR was quite large. Now to bring that FPR lower, we fixed the value of K. K is equal to log of n divided by log of 1 by P2. But by doing that, we brought down the FPR, but our TPR also came down. And for K, what we did, we used the AND function. We selected a family of H functions, and collision had to take place by all. That's why AND. Now to solve that, we came down to OR. We made tables of having such family functions, and then we made OR. And from there, we realized that with this K, and if we select L is equal to, then we come TPR is equal to 1 minus e to power minus theta. Theta we can select, and theta is correlated with the L. And your FPR becomes n into e to power minus theta, which is nothing but the value of L. From there, then we shifted to week 4, which was SVD, that how to reduce the complexity of SVD. From there, we came to fast SVD. And from the fast SVD, what we utilize the concept of randomization again. We utilize the same omega and how to do the SVD. I will recommend that I have not covered one part, iteration. So please go through the iteration. It is just simple. We are utilizing that A transpose to power Q into A. How do we reduce that? So that is one part. Then from SVD, then week 5 and week 6, we came to Laplacian, that clustering problem, that how to cluster. So in that, we have utilized the properties of Laplacian matrix to find the eigenvector corresponding to the second smallest eigenvalue. And that maps your entire data set into your linear space, where we can use the KNN to find that. With that, I have finished, friends. Thanks for joining in. In case of any question, I am open.
Can you just briefly explain the logic behind one of the PYQs? There were some graphs.
Okay. Okay. So I've got PYQs. Just you can tell me which PYQs there.
Yeah. Scroll down.
Yeah. This one?
No, not this one.
Okay. So, okay. I will share this document with all of you. Okay. This one?
Yeah, yes, this one.
Okay. So this is straight away from LSH. So LSH basically what it does, it changes in the buckets. So it was for the Euclidean distance, it had changed into the buckets. So you started with a sphere or a 2D and you made buckets. Okay. Similarly, when you go to, for example, two-dimensional buckets, so it will always linearly separate. Okay. Whereas the other two diagrams which it had given like this. Like this. So your LSH does not do like this. It will always give you the linear separation.
Okay.
Okay.
Sir, is it because of the hash function, which is A transpose X plus B, it is linear? Is it that's why?
No, it is not that. ATX plus B, if you see, it depends on the your dimensionality of A. If you're selecting A same, you can get a scalar value also. Okay, but that might be true, that ATX plus B. Any other question in this? So this I have already covered, that, the relation between K and L with TPR and FPR. Please try to remember this. This questions are directly from GA, but what Karthik was saying that, last term quiz 2 question paper was very easy. This time they will make it hard. So please remember the concepts, otherwise B is the standard correct answer always. Okay, so here I have covered here. I will share this document with you. This is the power iteration. We do y is equal to a omega, which is the first step. We take the omega. Now for I in the range of 1 by q, we do q is equal to orthogonal of y. So we take orthogonal of y, then do z is equal to q to a, then y is equal to az. So it keeps on happening till q, and final this q which is there now, this q we utilize to take b. B is equal to q transpose a. We do SVD of b, get this, retain the best k, and do the SVD of a. This is power iteration. Okay, any other thing?
You mentioned that if it will be mostly MCQ or we have to write in the answers, anything like that?
No, it was not mentioned.
Okay.
Yeah. Okay, thank you, Kunal, for joining. Thank you, Ravina.
Thank you, sir.
Thank you.
Yes, sir.
Bye, Surupi. Bye. Have a nice day. Bye.